First, let's talk about model interpretability. Understanding how our model makes predictions is essential for ensuring transparency. To achieve this, we used SHARP to analyze the most influential features in our model. The SHARP summary plot shows the top contributing factors with residence type, average glucose level, and age group emerging as key predators. The color gradient indicates how different feature values impact predictions. Blue represents lower values and red represents higher values. For example, high glucose levels tend to increase the probability of default, while certain residence types tend to decrease it. This global explanation helps us understand how the model is making decisions at an aggregate level. However, global insights aren't enough. We also need local interpretability, meaning we must explain individual predictions. This is where sharp force plot come in. The force plot illustrates how each features purchase a single prediction higher or lower. The base value represents the model's expected output, and features either add to or subtract from the baseline. In one particular case, we saw that age, BMI interactions, and work type had a significant impact on an individual classification. This level of explainability is crucial, especially in high-stakes decision-making where model predictions must be justified. To further validate interpretability, we used LIME. LIME builds an interpretable linear model around an instance to approximate how the black box model behaves. The results from LIME aligned closely with SHARP, reinforcing the importance of age, glucose levels, and work type in predicting default risk. By using both SHARP and LIME, we ensure that our model remains interpretable to different stakeholders. Data scientists can refine feature engineering, regulators can verify fairness, and business teams can better understand decision drivers. And now let's move on to fairness and bias detection. We don't want our model to be biased against any particular group, so we used FairLearn and AIF's 360 to measure fairness. We computed DPD, equalized odds difference, and statistical parity difference. The DPD is around 0.0227, indicates that positive prediction rates are nearly equal across groups, reducing concerns about demographic bias. The EOD of 0.0821 suggests only a small disparity in false positive and false negative rates between groups. Additionally, DI was around 0.7824 and SPD was minus 0.0104, both within acceptable fairness thresholds. To ensure further fairness, we checked whether sensitive features like gender or work type were major contributors to predictions. Sharp feature importance confirmed that gender had little to no influence on the model's decisions, supporting the fairness of our approach. Next, we assess the reliability of our model by analyzing confidence intervals and calibration curves. A 95% confidence interval of 0.1291 to 0.1456 indicates low uncertainty in predictions, meaning the model is stable and consistent. However, when we plotted the calibration curve, we observed slight overconfidence in probability estimates, meaning the model sometimes assigns probabilities that are not perfectly aligned with actual outcomes. To address this, we recommend applying Platt scaling or Ascending regression, which can correct overconfidence and improve probability alignment. This reinforcement enhances trust in the model's outputs, ensuring that predicted probabilities accurately reflect the likelihood of real-world events. Bringing everything together, we have successfully implemented responsible AI principles through explanatory, fairness, and reliability assessment. Sharp and Lime ensures that our model is transparent and interpretable, allowing different users to understand its decision. Fairness metrics from FairLearn and AIF 360 confirm that our model doesn't exhibit significant bias, ensuring ethical decision making. Finally, our confidence interval and calibration analysis provided insights into model reliability, highlighting areas for potential refinement. Moving forward, we recommend continuous fairness monitoring to detect shifts in data that may introduce bias over time. Additionally, refining model calibration techniques will further enhance probability estimation accuracy. So overall, our model aligns with responsible AI best practice, providing reliable, explainable, and fair predictions. By integrating fairness checks, interpretability techniques, and reliability assessment, we ensure that AI-driven decision-making remains ethical and accountable.